everybody. It's Friday, April 3rd, and this is Nighttime Mathematics Radio. It's a quiet Friday evening here. Nothing really new has arrived on Twitter. So let's take a few minutes up front here to see if anybody has any questions out there in this strange, quiet world where the classes have all stopped, but the homework goes on and on. If you have any math questions, remember just to tweet them to @NightMathRadio on Twitter. I'll try to help you right here live on the air. This is Nighttime Mathematics Radio. Stand by. Welcome back to the show, everybody. This is Nighttime Mathematics Radio. If you have any questions, you can tweet them to @NightMathRadio. I'll try to answer them live on the air. Now, what I'm going to talk about right now is something I started to do last night, and I made the worst mistake a math teacher could ever make, which is I just wrote down a random matrix without actually stopping to think, and by an amazing coincidence, I hit one of the interesting cases. So, let's look at it again, starting with the less interesting case, then going back to the interesting case we did last time. Here we go. Let's go back to the problem we looked at last time. The last time we looked at this problem, I was talking about eigenvalues and eigenvectors, and I idiotically wrote down the matrix 1, 1, minus 1, 3, which turns out to be really interesting. Like much more interesting than I intended. I'm going to write down a different random matrix and see if it gets a little less interesting this time, and then we'll come back to it. Now this time I'm going to write down a different random matrix. Again, say 1, 1, minus 1, 1. Here's a matrix. It takes a 2, just like when we did last time. It takes a 2 by 2 integers. It takes some 2 vector, and it feeds you out a new 2 vector, where the first entry is the sum of the 2 values in the 2 vector, and the second entry is the difference. Sorry, oops. Minus a plus b. Let's read the matrix. Minus a plus b. And the problem is, again, it's hard to see what that's actually doing to matrices. If I plug 1 in, I get 1 minus 1. If I plug 0, 1 in, I get... If I plug 0, 1 in, I get, 1, 1. So it's hard to see what this thing is doing. So again, we're looking for, just like last time, we're looking for vectors that when you plug them in, just give you back the original vector again, scaled in some way. Just like last time, you subtract both sides. We put in, we rewrite this as lambda times 1, 0, 0, 1 times AB. Subtract that from both sides, and we get 1 minus lambda, 1, minus 1, 1 minus lambda, AB is equal to 0, 0. And just like last time, we want this matrix to not be invertible, because we want this to have interesting solutions. So we want the characteristic equation here, 1 minus lambda, 1 minus lambda, plus 1 to be equal to 0. So lambda squared minus 2 lambda plus 2 is equal to 0. Now we say, okay, let's see, where does that have zeros? Well, again, it's a quadratic equation, so we just use the quadratic formula. Minus b, plus or minus, square root of b squared, minus 4ac, over 2a, which is 2. So this is equal to 2 plus or minus square root of minus 4 over 2. So this one has complex eigenvalues. That's fine. We can do that. 2 plus or minus 2i over 2. So this thing, the eigenvalues here are 1 plus I and 1 minus I. And now in each case, we just want to solve. Okay. In the first case, we have 1 minus 1 minus I, 1 minus 1, 1 minus 1 minus I, AB is equal to 0. When we do that subtraction, the 1's go away, and we end up with minus I minus 1, 1 minus I, AB is equal to 0. Oops, gone off the bottom of my sheet. And this we can just solve for. Minus A is equal to, sorry, minus A plus B is equal to, minus AI plus B is equal to 0, or minus A minus BI is equal to 0. And the cool thing about these are exactly the same equation. It doesn't look like it now, but let's see what happens if I start to solve for this one. In this case, I get B is equal to A times I. And in the bottom case, I get B times I is equal to minus A. Or if I multiply both sides by I get minus B is equal to minus AI. Or B is equal to AI. So here we have a real solution. We have matrices of the form. We can pick whatever we like for A, because remember, we're scaling anyway, so we can pick that. We don't have to normalize these things. So the eigenvector corresponding to 1 plus I is 1i. And that's cool. What do we have in the other case? Well, we have one minus 1 plus I. 1 minus 1, 1 minus 1 plus I, AB is equal to 0. So again, we have this, or rather this time we have AI plus B is equal to 0, or A plus BI is equal to 0, or minus A plus BI is equal to 0, I should say. So in this case, we have B is equal to minus AI. So in this case, the eigenvector is 1 minus I. And so these are the interesting directions. And units are complex. What does that mean? Well, what that really means is, and this is really interesting bit. What this means is this is really a rotation. This is what a rotation looks like. When you see you have complex eigenvalues, what you really mean is if you apply it twice, you end up negative. So what this tells us is this thing is really a rotation. If you apply it twice, you end up looking the other way. And if you look at what this thing actually does, that is in fact exactly what you expect here. So that's a normal case. What happened yesterday? Well, yesterday, remember, we ended up in a really weird case. We had exactly one eigenvalue and exactly one eigenvector. So what's going on there? The answer is that does happen sometimes. There are some matrices for which there really is only a single eigenvector. That means this matrix is not an even, and the fancy word gets used to, this matrix is not diagonalizable. There's no normal basis under which this vector can be made diagonal, which is cool. And if you go on, you'll see what this means. If you go on to the point where you're looking at Jordan normal forms, you'll see this thing has a Jordan normal form with a two-dimensional Jordan block. That's a bit later in the subject. This is Nighttime Mathematics Radio. Let's go back to Twitter. And it's still looking like a quiet night, since after all, it's a Friday night. I think people are tired. But one more question did come in, so let's take a few minutes to wait for more questions to come in. I'll answer the last thing that I've seen on the air, and we'll go on from there. This is Nighttime Mathematics Radio. Welcome back, everybody. Well, it's a quiet night here. There's probably no reason to go on from here. The other question came in was answered adequately by someone else, so there's no reason for me to do it here on the air. So I think at this point, it's maybe time to end the show. So in this weird world where the math homework goes on, but the classes have stopped forever, and all you have is for help is voices in the darkness talking over some of the weirdest loops that Apple's ever made free. Feel free to tune in any weeknight at 9 p.m. Pacific, and I'll try to help you out. This has been Nighttime Mathematics Radio. See you everybody next week.